Okay, let's talk about this, and then we're going to kind of build on this idea and go forward from there. So this said we're using exponential growth, so we want to use our exponential growth formula. This is the one we've been looking at the last couple days, where we have a beginning amount, some multiplier. The exponent means how many times are you going to multiply it, and then y is just the ending amount, right? So there's 4 pieces of information here. You were given 3 of them, right? So how many rabbits did we end with? 712, right? How many did we begin with? 4. What is the multiplier? That's the question that we were trying to answer, right? We don't know what the multiplier was. It's saying what was the daily rate of change. So I'm just going to call that B as in boy. And then the exponent. How many times were we going to multiply that? Well, some of you either probably put 30 or 31, depending on how you read it. That's why I gave it approximately. It would be 31 or 30 times. How many times would we multiply it? I think we would do it 30 times in order to get to day 31, right? If I'm standing on day 1, how many times do I have to move to get to day 31? I'd have to move 30 times. So I would multiply it 30 times. So we've got this equation and we want to solve it for B as in boy, right? So, you know what? I think I forgot my calculator today. It's down in my office. Well, you guys are going to have to help me out. What's 712 divided by 4? 178. So 178, all I did is I divided both sides by 4. 178 equals b to the 30. We're trying to solve for b to the 1. So we did this the other day, like multiple times, right? How do we do it? I want to take each guy to the 1/30th power, because then multiplying properties of exponents, 30 over 30 would give me b to the 1, so that's what I'm interested in. So b is equal to, so this is where if you didn't have a calculator, you'd be swimming in it here, right? So what is 178 to the 1/30th power? I think it's 1.188 or something like that. 1.189? Yep. Okay. So b is equal to 1.189. So that means our multiplier is 1.189. Well, 100% of it would be, if you started with 4, we're assuming none of them died off. We didn't lose any. We get those 4 plus the multiplier. So we're multiplying times 1.18. So the growth rate is 0.189, which is approximately 19 if you round it. 19% is what you should have figured out. Now, that was a multiple choice item. If you wanted to, you could have taken, I don't remember what the other options were, 11 or 13 or 25 or whatever it is. You could have taken 4 times 11% or 1.11 to the 30th and saw how many rabbits it produces. You could have tried each one and worked it that way. This would be what I would hope you would be able to do, is just cut to the chase. Is out of your 4 components, you know 3 of them. And you can calculate it. Where we're going today, I want you to think about the exact same problem. Let's say that it gave you the 712 and the 4. So let's say we're going to end with the 712. We're going to start with the 4. And let's say it gave you the 1.189. You know, let's say the problem said they are increasing by 18.9% every day. So then you could, from that information, you would know the 1.189. You would know the multiplier, right? But let's say they didn't tell you this. Let's say I crossed this out. And I said day question mark. So this time I'm changing the information that's given to you, right? This time I wouldn't be solving for the multiplier. I would be solving for the exponent x to see what, how many days did it take to get to 712 rabbits. You guys see the difference? Okay, so think about how you might solve that guy. I could still divide both sides by 4, right? Like that and like this. So what do I get here? 178 equals 1.189 to the x power. How do you solve that guy for x? Do we have a solving procedure for that? It's not a square root, because a square root would be to the power of 2 or the power of 1/2. You're saying like to the x root?
Yeah.
Yeah, is there an x root? What do you think?
Using logs.
Log, oh my gosh. What does that mean? Let's come back to this in a little bit. We're going to come back to this. I'm going to give you like a little exercise to practice here. Let's see. How should I do this? Here's what I'd like you to do. On a piece of scratch paper, I want you to see if you can solve for x. Don't worry, you won't be handing this in. Notice that for each of these, the x that we're trying to solve for is up in the exponent. We haven't done that yet this year in this class. All the x's that we've been solving for have been, on the main line, it's been x to the first, it's been x squared, or it's been x raised to some power. But we have yet to solve any problems where x is actually up in the exponent. My hunch is most of you are going to be able to handle number 1 and number 2 quite easily. 3 and 4 are a little more challenging. Anybody want to yell out an answer for number 1?
3.
It's not 3. 3 to the x power, not 3 times x. So 3 to what power gives me 9? It's 2. 3 squared equals 9. How about number 2? It's a 4. 2 to what power gives me 16? Well, 2 times 2 times 2 times 2. If I do it 4 times, I get 16. So the answer is 4. Okay. This is a terrible day for me to forget my calculator.
Do you want to borrow mine?
Maybe in a little bit. I can't run one of those Casios. I need a TI. Does anybody have an answer for number 3?
2.33.
2.33 roughly? Yeah, it's actually 2.334717 blah blah blah. It's a decimal that goes on forever. Now some of you are thinking, how in the world did Noah figure that out? Some of you knew how many of you knew how to do that? Noah obviously knew how to do it. Did you know? Kinda? Anybody else? Going once? Going twice? Oren, thank you. Okay, so we're going to learn something today. Before we reveal the answer to number 4, how about we just try to estimate it? Like, what number do you think it's close to? The real answer is a decimal that goes on forever. So, but if you had to estimate it, x is going to be about what? 3.5. What made you think that?
Because 2 times 2 times 2 is 8, and then there has to be one more.
Yeah. So, what would happen if you thought x was equal to 3? If you plug it in, it'd be 2 raised to the 3rd power. Well, what is 2 raised to the 3rd power? It's 8. What are we trying to get? Trying to get 9. So Katie's right. It's not 3. She knows that it's a little bit more than 3, right? But what happens if you tried 4? What's 2 to the 4th? That's 16. And we're only trying to get to 9. So 16 is way too big, right? So we know our answer is somewhere in between 3 and 4 because 3 is too small and 4 is too big, right? So is it going to be closer to 3 or is it going to be closer to 4? Katie said 3.5. She split the difference. Is it closer to 3 or closer to 4? It's closer to 3. And you could try it in your calculator. You could try, say, 3.1. Punch that in. Punch in 2 raised to the 3.1.
8.57.
So we're close. 8.57. Try 3.2.
9.18.
9.18. So what did we just learn? It's between 3.1 and 3.2. So now what could we try? 3.15? And that again, we could do this over and over and over again. Are we ever going to get our calculator to spit out 9? No, because the answer is a decimal that goes on and on forever. But do you see how you can kind of estimate what you think it might be? It's 3.169925 blah, 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 blah. Okay? And for those of you that don't know how we did that, pay attention. Okay? Here's a little way to get us going here. We've been talking about exponential growth. Remember when AV was going to give us that payment plan for that job? Right? Remember the rabbits? Remember the deer? Remember these things that are growing? Let's fill in the blank here. An exponential growth function starts growing very slowly, but over time it ends up growing very quickly, fast. I don't know which word I have in there. Quickly. Right? Starts slow, and then it takes off and goes fast eventually. Right? So now we're going to introduce a new word, which some of you have heard before. And let me preface this with, I've been teaching math for 14 years, and when math students hear the word logarithm, they immediately go into a panic because it's like this some unbelievable complicated thing that they don't even want to. It sounds complicated. Okay? I'm going to try to decomplicate that for you and have you just understand what a logarithm is. And it's nothing more than an exponent is all it is. If you understand exponents, you understand logarithms. Okay? So here we go. A logarithmic growth function starts growing very quickly, but over time it ends up growing slowly. So what's the relationship between an exponential function and a logarithmic function? They're inverses of each other. And we've been talking a lot about inverse functions. We've done it 2 different days in class now with inverse functions. If you think all the way back to when we watched the Ace Ventura video and we did the directions to that person's house and all that kind of stuff, these are going to be inverse functions of each other. So here's a little diagram, and I've been drawing this diagram on the board several times this year. If we have some set of numbers, these are my inputs. Let's just look at the top for now. Ignore the bottom. If these are my inputs, and my inputs go into some function f, and then they come out of it, these are my outputs, right? These are my x values, these are my y values, domain and range, okay? Well, if I did that, and now if I come back the other way, if I make these the inputs, and I come back into f inverse, I get right back to where I started. So A goes in, produces B, B goes into this one, right back to where I started. That's the diagram that I drew when we talked about inverse functions, right? So what we're going to have is we're going to have our original function is an exponential function, just like the rabbits one that we just worked on. And then our inverse function coming back is going to be a logarithmic function. And we can get right back to where we started. Here's what it looks like graphically. The green one is the exponential. It starts growing very slowly. It's not going up very fast at all. And then after a while, it takes off and it gets really fast, just like when AV's payment plan on that Desmos we did the other day. Notice the blue one is the logarithmic. See how at the beginning it's really steep? It's going up fast right away. And then over time, it slows down. And by the time it gets to the end, it's not going very fast at all. And the same thing with all of these inverse functions that we've done. If you put this dotted line through y equals x, if that were a piece of paper and you were to fold it over, the one would fold right on top of each other. They're mirror images of each other. The x coordinates become y coordinates and the y coordinates become x coordinates. So probably the most difficult thing for most students with the logarithms is, well, first of all, conceptually understanding what it is, okay? But the notation can get a little bit dicey. So these are just snapshots out of your textbook. A logarithm, can you guys find the button on your calculator? There's a button, LOG, log. Everybody found it?
I have a more complex one.
You might have one that also says LN, which might be the shift of the log. What does yours say?
LOG, then the sub, and then that one.
Yeah. So yours asks for the LOG and the sub. Depending on what kind of calculator you have, we'll talk about that. So, logarithms and exponents are the same thing. It's just a different way to write it. Okay? So if you had b raised to the y power equals x, b to the y power, b to the y equals x, that's the exact same thing as saying logarithm base b raised to the y power gives you x. You see how it makes that little circular kind of notation there? So if I look at the one on the bottom, log base, the way we read this is log base b of c equals a. Log base b of c equals a. So what does that mean? Notice I said log base b. b is the base. A is the exponent, so b the base raised to the exponent a gives us a value of c. Let's have you practice on a piece of scratch paper really quick. Fill in the 5 blank spots. Here's something in logarithmic form. I want you to give me the equivalent in exponential form. Same here. Then I give you 3 that are in exponential form, and I want you to give me the equivalent in logarithmic form. They're the exact same thing. They're the same value. They're just written in 2 different notations. And we'll talk about why that is. So fill in the chart. Identify your base, identify your exponent, and then identify the number that results when you take said base to said exponent. I have to go get my calculator. Time me.
Can we how do I do this now? Oh, I think see you, but I have well.
I can fucking do it like no other.
I gotta switch it.
That and figuring it out.
Nice work.
Don't ask me fucking how.
Okay, here we go. Let's start at the top. Anybody want to share an answer?
Sure.
Go ahead, Luke.
10 to 6.
10 raised to the 6th power gives me... Oh, terrible writing.
Yeah. 100.
10... Oh, boy. Let's try that again. 10 raised to the 6th power equals 1 million. You guys agree? If you were to punch 10 caret 6 into your calculator, you would get 1 million. Okay? Second one?
5 squared equals 20.
5 squared equals 25. So again, these are saying the exact same thing. 5 squared equals 25. Now let's go the other way. The one thing we know for sure is we have to use the notation log, log. So I could fill that in on all of these. Log, log, log. Okay. Now the only thing we need to do is we need to identify our base, identify our exponent, and identify the number that results here. So how about the first one? What's my base? 3. So it's log base 3. And we usually write that down kind of in the basement, if you will. It's a subscript. Log base 3 of 9 is equal to 2. So if you do the little circular thing, it'd be 3 raised to the 2 power gives me a value of 9. Think of it that way. What's the next one? Log base 5 of 125 equals 3. And the last one, log base 2 of half, so I'll put it in parentheses here, equals -1. Like that. Okay, let's try this one. If y equals log base 121 of 11, without using your calculator, can you tell me what y is equal to? It's not equal to 2. Otherwise, if it was 2, we would be saying 121 squared gives us 11. So you got your number and your base mixed up, right? It's not 2, it's half. Yeah. The square root of 121 gives us 11. And we know that square root is the same as taking it to the 1/2 power. So I would say 121 to the 1/2 power is what gives me 11. So therefore, y is equal to 1/2. Wow. Y is equal to 1/2. Okay, how about the second one there? -5. Very good. The only way you would have known that is you see the 32 and you said, well, 2 to the 5th gives me 32. So how do I get 1 divided by 32? So you would have to understand the properties of negative exponents, right? So if 2 to the 5th is equal to 32, then 2 to the -5 actually equals 1 over 32. So my answer is -5. Y equals -5. Okay. On your calculator, you probably have a button. Depends on if you have a Casio or a TI. I have a button on my TI right beside my 7 key called log. You guys have that? When you hit the log button, notice on my calculator, it doesn't ask for a base. There's nowhere to put in a base. Now, Katie, you just showed me on yours, it's log, and then it has the little subscript, and you can type a number in there. Mm-hmm. So depending on what kind of calculator you have, it doesn't mean that Katie's can do some kind of computation that mine can't. There's a quick and easy workaround if you understand log, which is why my calculator doesn't even have that button, because you don't even really need that button, even though it's there, which is fine. When you write log and you leave the base part empty, you don't write a base number in there, it's base 10. We just assume that it's base 10. So these two things mean the same thing. Log is exactly the same as log base 10. Same thing. It's just like when we think of x. We don't write it as x to the first power. We just call it x and we assume that it's to the first power, correct? Same thing here. When we write log, we just assume that we mean log to the base 10. So, how would you evaluate this? Log of 1 million.
6.
It's 6. How did we know that? The 10 is missing, but we know there's a 10 right here. So it's saying 10 raised to what power gives me 1,000,000? And the answer is 6. And we can try it on your calculator too. Let's do this other one first. Log of 123. So it's saying 10 raised to what power is going to give me 123? You see how this one's a little more difficult than the other one? The other one we could do in our head. Why? Because the number we were looking for just happened to be a perfect power of 10. 10 to the 6. Our answer was a whole number. The 123 doesn't work though because 10 squared is 100, too small. 10 cubed is 1,000, too big. So our answer's got to be somewhere in between 2 and 3. Probably closer to 2. Okay, so how do we do it then? I would go to log. First let's do the million one. Log 1, 2, 3, 4, 5, 6. Did I do that right? Log of 1,000,000 is 6. We already got that one. But we could have done that one in our head. This one's tougher though. Log of 123. What's it going to be? 2.089. You guys are going to find this hard to believe, but when I was in high school, we did not have calculators that would do this. So how did we know what log 123 was? We had textbooks with tables of numbers with 40, 50, 60 pages, and you'd have to flip through and you'd have to find which one you were looking for. Now, I'm not that old, but that's actually how we used to do this before these calculators became mainstream, right? Because you can't do it without a calculator or a table. The mental math computation to figure out that it's going to be 2.089905 is darn near impossible without a calculator. Okay? So understanding where your logarithm button is very important. Okay, let's try one more slide here. Let's try, okay. We also have what we call natural logarithms. So if I write this guy up here, your calculator can handle 2 of them. We know that log is log base 10. Remember that fun number e that we talked about the other day? Your calculator can handle log base e. But we don't write the e. The shorthand of it is ln. And somewhere next to your logarithm button, you should have an ln button. Mine is right below it. You guys see it? So those are your 2 logarithm buttons. So what the first one is saying here, ln of 500, it's saying log base e of 500. Another way to say that is e raised to what power gives me 500? E raised to what power gives me 500? Well, it's going to be some awful decimal. So again, we're going to want to utilize our calculator. So let me, we want the ln of 500. Okay, so I'm going to use my ln button. E raised to what power gives me 500? About 6.2146. Are we good there? What was the other one? ln of negative 500? Think about that for a second. Did you get an error? Can you explain why you got an error? Is it because your calculator's broken? It's not because your calculator is broken. What is e? It's a number. It's about how big? 2.718. So think about it. Can I take a number, it's about 2.718. Can I raise it to some power? That's a positive number raised to some power, meaning I'm going to take 2.718 times himself some number of times. Is there any way to take this number times himself some number of times and end up with a negative number? That's impossible, right? So what did we learn here? Whether it's log or ln or whatever, you can never take the logarithm, regardless of what base it is, you can't take the logarithm of a negative number. You can't produce it, right? Subsequently, you also can't have logarithm of a negative base. Remember when we talked about our rules on b with the exponents the other day? We said it had to be a positive number and it can't equal 1, right? So you would never take logarithm of like -2 and then raise it to some power and try to get a number, because what's going to happen? You can't use -2 as the base in an exponential equation, right? So the same rules that held true for b when we did exponential are going to be the same rules that hold true for b when we do it as a base in the logarithm. It's got to be a positive number, and it can't equal 1. What happens if it were to equal 1? 1 raised to what power gives me some number? Well, 1 raised to any power gives me 1. So it doesn't make any sense to use 1. Okay. So what you're going to get a chance to do here with your quizzes and your homework for now is to just basically work with exponential form and logarithmic form and transition back and forth, get a little practice going back and forth so you understand the notation, and then things will make a lot more sense. Underneath course docs and links, you don't have to go there right now. I just want to show you what's there. Underneath 6.3 and 6.4, this is the PowerPoint that we just did. This is a 7-minute YouTube video of a guy basically going over what we just went over with logarithmic form and exponential form. So if you get stuck, I picked out this video because it's only 7 minutes long, and I think the person on there does a pretty good job of explaining logarithmic form and exponential form. So I just wanted to make you aware of that. So let's go back to this rabbit problem that we did earlier when I said we were going to come back to this. Okay. We are faced with the following equation that we have to try to solve. Anytime the variable that you're trying to solve for is up in the exponent, that is probably going to be a scenario where you're going to end up using logarithms, unless it's one that you can do in your head. So I'll give you an example really quick of one that you can do in your head. 2 to the x is equal to 64. I could use logarithms if I wanted to, but I don't know if I have to. Because I can just say, okay, 2 times himself, how many times gives me 64? And the answer is x equals 6, right? 2 to the 6 gives me 64. So that's not too bad. But what happens if I gave you 2 to the x equals 63? See how that one's easy and one's not? The answer to this guy is going to be just shy of 6, like 5.8 or 5.9 or something like that. So, can you do this one in your head? I hope not, because if you can, you have no business in being in this class. So how are we going to do it? We're going to use logarithms, right? So, let's look at this. This is saying, let's just look at this right-hand side. How could I rewrite this in logarithmic form? Log, what's my base? 1.189, right? 1.189 raised to the something power. 1.189 raised to some power that I don't know what it is gives me the number 178. See what we did there? We just rewrote it in logarithmic form. So that table that I gave you guys about 10 minutes ago and you filled in the table, that's all we did. We took one that was in exponential form and we rewrote it in logarithmic form. Okay? So, how in the world are we going to handle this now? Yeah, but what about those of us that don't have a button? Because like my calculator only had 2 buttons. They were log base 10 and log base E. Right? log base 10 and log base e. But the problem I have here is log base 1.189. That's not 10 and it's not e. So how do I handle this? It's actually quite simple, and we'll talk about why this is. It's what we call our change of base formula. If you just take log of 178 divided by log of 1.189, you'll actually end up with the number that we're interested in. So on your calculator, and now you got to be very careful when you do this. And let me show you why. I'm interested in punching this into my calculator. Okay? The novice student who doesn't know what he or she is doing goes like this. Log 178 divided by 1.189. Do you see the problem with that? That's taking the logarithm of a fraction. I don't want the logarithm of a fraction. I want the logarithm of a number in the numerator divided by the logarithm of a different number. So I don't want to do it that way. I want log 178. Now I can either hit enter right here and figure out what decimal it is. That's my numerator. And then I can divide it by log 1.189. And the answer is 29.9333. Now think all the way back to when we did the rabbit problem. It was what? How many days did it take us to get that many rabbits? 30. But why is my answer not 30?
Because it was off on the first round. The decimal.
The decimal, I rounded it. This 1.189, I just rounded that. That was a decimal that went on forever and ever and ever, right? So, but now do you see how that 30 comes out, 29.93? It would have been 30 days, except for my rounding. So the other way to do this would have been log 178 like that, and then put that whole thing in parentheses. If I wanted to do this all in one calculator sequence, log of 178 divided by log 1.189. I could do it all in one line. I think it's easier to do it the other way. Figure out what your numerator is, figure out what your denominator is, and go from there. We're going to be doing more of this when you come back from break. I'm going to give you guys both Friday and Monday off. So we will see you on Wednesday. I will stick around for a while. We still got 5 minutes of class left. If you're having issues with you had an assignment due today. Did you guys know that? It was your GeoGebra sliders and getting that to work. If you have any questions or issues on that, Oren and I are going to hang around for a few minutes. So feel free to flag us down. Otherwise, have a great break. And we'll see you on Wednesday.